Good evening, and thanks for joining tonight's TI Technology webinar hosted by Texas Instruments. Where tonight we're going to take a look at some calculus resources, specifically results from some of the most recent AP Calculus exam, and then how you can use technology to help your students learn AP Calculus content and calculus content in general. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI technology to make tough-to-teach, tough-to-learn concepts accessible to all my students. Tonight, I'm excited to be joined by our two panelists, Steve Kokoska and Tom Dick. Steve is a recently retired professor in the Department of Mathematical and Digital Sciences department at Bloomsburg University. He is a former chief reader for the AP Calculus reading and a member of the development committee. Steve's an active T-Cube instructor and College Board consultant with recent workshops in China and Singapore. He just published an AP Calculus text and the third edition of his introductory statistics text. Steve, it's great to have you with us tonight.
Thank you very much, Mike. Great to be with you and Tom again. Always enjoyable and fun to talk about AP Calculus topics. Thanks for arranging this.
And Tom is a senior math advisor for Texas Instruments and also professor and former chair of the math department of Oregon State University. He has served on the editorial panels for the Journal for Research in Mathematics Education and the Mathematics Teacher Educator. He remains active in the College Board's AP Calculus program, and in 2008, Tom was inducted by the Oregon Council of Teachers of Mathematics into the Oregon Mathematics Education Hall of Fame. Tom, it's great to have you with us.
Thanks, Mike. And it's great to be here with you and Steve, and looking forward to talking about AP Calculus tonight.
We're expecting a large crowd, so your audio is muted. Feel free to send any questions to Steve or Tom using the Q&A window on the right side of your screen. We'll also use the chat window to send general messages. As a reminder, the session is being recorded, and we'll provide a link to the event certificate of attendance at the conclusion of the webinar. We hope you don't have any audio issues tonight, but in the event that you do, try selecting Communicate from the very top of the WebEx menu and choose Audio Broadcast. At this point, Steve is going to discuss our agenda.
Thank you very much, Mike. Well, we've already done welcome and introductions. Our plan is to just remind you about what TI-Nfocus AP Calculus, what that project is all about. And we'll just remind you of the videos that are available that correspond to the years 2017, 18, and 19. I'll just briefly discuss those videos and what they're about. And since 2020 was such a unique year, we're going to give you a sneak preview of what we've done this year. Our TI-Nfocus AP Calculus videos are a little bit different. So we're going to show you, give you an idea of what they look like this year, and they revolve around mock exams. I'm going to do a lot of that, but eventually I will pass the screen over to Tom, and he will show you some of the technology videos that he's constructing for our mock exams to correspond to our mock exams. And throughout all of this, we really do sincerely welcome your questions. Please type into either the chat room or I guess, Mike, the Q&A window, and we would be happy to answer them.
Steve, thanks so much. All right, Steve, you should have control. Feel free to share your screen.
All right, here we go. Give me 1 second to make this just a little bit bigger, and let's see. How's that? Okay? All right, well, here we go. This is all about TI-Nfocus AP Calculus. This is a collection of resources focused around AP Calculus and the AP Calculus exam. Just again, a quick kind of refresher of what we've constructed so far. This is very easy to access. All of these resources are on the education.ti.com website. They are easily accessible through a tab right here. If you click on Resources, you will get a submenu here, and all you need to do is to click on TI-Nfocus AP Calculus. Tom reminds me frequently that if you happen to do a Google search on TI-Nfocus AP Calculus, this is one of the first sites, I believe, that appears. If you click on TI in Focus AP Calculus, you'll get a window like this, which tells you a very brief description of these TI in Focus resources. And beneath that, these resources are right now organized by topic and year. This is a screenshot from about a month ago. I don't believe that they've added the 2020 information yet, but this is what it looks like. You can actually search these resources by topic and also by year. And again, 2020 will be added very shortly. I guess they are in the process of adding some of those videos. We haven't quite finished all of them yet. And if you get to a specific free response question, we have actually taken each free response question from the released exam for 17, 18, and 19, from the operational released exam. And we've taken the 9 free response questions and constructed 5 videos associated with each one of those questions. I've worked on what we call these resource videos, and the first one over here on the left-hand side has to do with the scoring of the exam, the scoring guidelines. So what I do is I work through these scoring guidelines, examining how the points are distributed. I talk about some interpretations of the scoring guidelines, some ideas, some items, some topics that you don't really hear about unless you're actually at the reading. I talk about where points are actually earned. What does the student have to do? Where's that line in the sand where they can earn a point? I talk about some common student errors, and I give some example student responses and how each of those would be scored. In the middle here, my second video associated with each free response question has to do with technology solutions and extension. And the idea here is that the scoring guidelines do indeed give a solution to each problem, but they tend to be pretty succinct. And so what I've done in this video is I've worked through the solution to each problem in a little bit more detail so that we can all see where the solutions are coming from and how to solve them, and sometimes from a little bit different angle. And in addition to that, I provide what I call extensions, extra examples or extra questions that you can use in your AP Calculus class. These free response questions tend to be very rich in nature, and Tom and I have talked about this frequently. In the construction of a free response question, they generally start out in the development committee with 8 or 9 parts, and they're whittled down. They tend to be very rich, lend themselves to a lot of questions, and so we've added some extensions to these and provided some extra problems. And one thing that I do in this video is that even if the free response question is not a technology active question, I still explore the use of technology, either or both. How do you solve the problem using technology? And how do you explore this topic a little bit more in depth with technology? And then on the right-hand side, my third video is what I call a topic summary. I take one of the topics that is addressed or needed in order to solve part of the free response question, and I present a content lecture, something that you might be able to actually use in class, something that you might be able to assign to your students to watch, something that you could use to get some ideas for how to present a specific topic. Now, in addition to those 3 videos, Tom has also constructed some great technology videos associated with each free response question. One that's geared towards the TI-Nspire CAS version, and one the TI-84 plus CE graphing calculator. And these are technology videos that highlight, again, how do you explore one of the ideas in these questions, or specifically, how do you use the calculator to solve the question, even if it is not a calculator active question. So those are the 5 types of videos associated with each of the free response questions for those previous 3 years. But as I said, 2020 was very unique for all of us, and the AP Calculus exam was very different. The College Board will not allow us to use any of the questions on the 2020 exam. You probably know that there were several forms. None of the questions are going to be released. They're all going to be behind the audit wall. or placed in AP Classroom. So those of you who have passed the audit or have access to the classroom can certainly find those questions, but you're not going to find them on AP Central. You're not going to find the scoring guidelines on AP Central. However, the College Board did give us permission to create some mock exams that were very similar to what the College Board or what ETS offered in 2020. So Tom and I created an AB and a BC mock exam similar to what was done this year. 2 questions for AB, 2 for BC. One of them in each is graphical, one of them is tabular. And if you're familiar with what happened in 2020, boy, there were lots of points available. And so we've got lots of parts here. So my videos correspond to, well, I've broken up each question into parts, and I discuss the key concepts that are needed, the key AP Calculus concepts needed in order to solve this question. So that's kind of like a content summary. Then I present a detailed solution. How do you actually take these concepts, put them all together to solve the problem? Then we present some scoring guidelines that Tom and I have developed from our experience at the AP Reading, from our experience as serving on the development committee. So these are what we think the scoring guidelines would look like for our mock exam. And we've also drawn upon our experience as participating in the 2020 reading. And I also present some interpretations of these scoring guidelines. These are some scoring notes to help you, our students, prepare for the next AP Calculus exam and how they can earn some points and get them from a 4 to a 5 or a 3 to a 4. So what I'm going to do is to go through, give you an idea, a sneak peek at one of these videos. And this has to do with our question AB1. I'm not going to go through, of course, every question, but I am going to go through a couple of parts. And I think I picked a topic that often lends itself to lots of questions. So Mike, let me know if any show up in the window there. This question is a graphical STEM problem. It has to do with a continuous function f with domain -2 to 9. And the graph of f is given here, and it consists of 3 line segments and 2 quarter circles, kind of a typical sort of a graphical STEM we've seen frequently. And if you take a peek down here at the bottom, there is a new function g defined in terms of a definite integral. It's 0 to x of f of t dt, for x between -2 and 9. So that's the STEM of the problem. And we've got lots of questions here, and I'm not going to read through all of these. This question will be available on TI and Focus AP Calculus. If it's not there yet, it'll be there shortly. But what I'm going to do is try to take a look at C, D, and E in here if I can. So bear with me. This is a little bit about what the slides look like that correspond to this video. And I'm going to talk a little bit about what's on the video. So in part C, the student needs to find the open intervals on which G is increasing and concave down. And there's one of those phrases that we often see in AP Calculus exam questions. They need to provide a reason for their answer. So what I do is I think a little bit about this, and I think about the key concepts that students need in order to answer this question. And I'm going to give you a little bit of a background and a little bit of a content presentation. So first of all, here's a definition of a function increasing or decreasing on an interval I. Now, I want you to note that this definition is given in terms of an interval as we move left to right. It does not involve, the definition does not involve the derivative of f. However, down here, the derivative of f can indeed reveal where a function is increasing and decreasing. And here's the statement of what I might call the ID test, or the increasing-decreasing test. And we'll take a closer look, what I call a closer look at this in just a minute. But it says that if f prime of x is greater than 0 on an interval, then f is increasing on that interval. And if f prime of x is less than 0 on that interval, then f is decreasing on that interval. So if you take a look at this figure, here's a little bit of a closer look at this ID test. If you take a look at this figure, here's a little bit of a justification for this result. Let's consider this graph. I don't think I put this in here, but this is a graph of y equal f of x in the blue. So if we take a look at values of x between x equal a and x equal b, and x equals c and x equal d, and we draw the tangent lines in there. I'm sorry, this is kind of hard to do here, but there's a tangent line in green. There's another one there. There's one over here and there's one over there. I drew a couple of them in. The tangent lines to the graph of f in those intervals have positive slopes, and therefore f prime of x is greater than 0. Now, similarly, if we look between x equal b and x equals c, I'm just going to try to scribble one of them in. There's one right there. How about that? The tangent lines to the graph of f have a negative slope, and therefore f prime of x is less than 0. So I think there's some good visual justification for why that increasing-decreasing test works. And by the way, you can actually prove this increasing-decreasing test. It's really not that bad. It's a proof that uses the mean value theorem. And I won't do that with you, of course. But you know what? It's a nice application of the mean value theorem. And I think it's a very student-accessible proof. I think you can do that in class. You might even be able to assign that to some of your students. All right, well, in order to solve part C, we also need to recall the definition of what it means for a function to be concave up or concave down. And I need to connect this definition to the derivative of the function. So here's my definition. F is concave up at a value a, if the graph of f is above the tangent line to f at a, for all x in a neighborhood containing a, but not necessarily equal to a. Similarly, okay, f is concave down at a if the graph is below the tangent line for all x in a neighborhood of a. Now, I'm going to draw a couple of pictures of this definition to support this definition in a minute here, but here's a closer look at this. You know, I use this phrase neighborhood, and some people cringe at that, but a neighborhood is really easy. It's just an open interval containing A. And it doesn't have to be a symmetric interval about A. It's just an open interval containing A. And note here that the way that I've defined this, concavity is defined in terms of a single number, not an interval. Not an interval like increasing and decreasing. So for me, it's okay to say that the graph of a function is concave up, concave down, or actually can have no concavity at a specific value or at a specific number. Well, I can also visualize this definition, and here's a couple of graphs here. Here's some graphs that illustrate, I hope, this definition of concavity. And emphasize, I think, the idea that concavity is defined at a value, not over an interval. So over here in the top left-hand side, here the graph is concave up at a value x equal a. If you take a look here on the x-axis, there is a neighborhood. Now, I've drawn it so that it sort of looks symmetrical, but once again, it doesn't have to be. There's a neighborhood of a, an open interval, in which the graph of f lies above the tangent line. I think I can see that. The green line is the tangent line, and the graph of f is above the tangent line in that neighborhood. Over here on the right-hand side, this is an example where f is concave down at x equal a. As I draw the tangent line at x equal a, there's a neighborhood in which the graph of f is below the tangent line. And down here in the bottom left-hand side, this is an example in which the graph of f has no concavity at x equal a. That sounds kind of funny, but it has no concavity. Now, I don't mean to imply that this is the only instance in which this occurs, but this is an example, one that I think I can draw and justify easily, pretty easily anyway. We cannot find a neighborhood of A containing A so that the graph of f is entirely above or entirely below the tangent line. Therefore, according to my definition, the graph of f has no concavity at A. All right, so there's a concavity test here. The second derivative can be used, as you know, to help us determine in the intervals of concavity. If f is concave up, as x moves from left to right, the slope of the tangent line is increasing. So this means that the derivative, f prime, is an increasing function, and therefore its derivative, f double prime, is positive. Very reasonable, very logical. Similarly, if f double prime of x is less than 0 for all x in an interval, then the graph of f is concave down on I. So if you bear with me, let me take a closer look at this. We'll put all of this together. We'll eventually get to solving the problem. Here's a closer look at this concavity test. So the way that I see it is this allows us to draw a conclusion about concavity of the graph of f if f double prime of x is greater than 0, or if f double prime of x is less than 0. We need to consider separately those numbers a, where f double prime of a is equal to 0, or where f double prime of a does not exist. Now, just a reminder, the graph of f is either concave up, concave down, or has no concavity at a number a. And although we don't really need this concept in this problem, it does seem reasonable here to remind you about the point on the graph where f changes concavity, or these inflection points. Mike, any questions so far? Nothing?
Not yet. You guys are doing such a good job that
Thanks for saying that, Mike.
it all makes sense.
All right, I'm going to add something down at the bottom here. I'm not going to write this, but I do want to add a number 4 here. You know, one of the ways that concavity has been tested on the AP Calculus exam most recently is that we take a look at a derivative f prime. And I just want to remind you of that. And that is that if f prime is increasing, I think I stated this already, but if f prime is increasing, that means f double prime is greater than 0, and therefore f is concave up. That's the notion, that is a notion that has been tested here frequently on the exam. Similarly, if f prime is decreasing, so if the graph of f prime is decreasing, then f double prime of x is less than 0, and therefore f is concave down. All right, thank goodness. Let's see if we can put all of this together here and finally get back and solve this problem. I have reproduced a graph here. I might do a little bit of scribbling on here. Here's the graph once again of f, which is equal to g prime. And I apologize for this, but in one of the other videos here, I've certainly talked about the fundamental theorem of calculus, but that's also an important concept here. The student has to recognize, I think I can scribble that in off to the side here. We have g of x was equal to the integral from 0 to x of f of t dt. And the student has to recognize that g prime of x is equal to f of x. And that's the fundamental theorem of calculus, traditionally called, I think, part 1. So I have to find these intervals, I think, where g is, let me see if I've got this right, increasing and concave down. So let's see, g is increasing where g prime, which is equal to f, is positive. So I have the graph of f in front of me. So I'm going to see where it's positive. I don't know if this is going to come out very well, but here over that interval, -2 to -1, 2 to 7, it's positive, and 7 to 9 is positive. Now, what we've learned here by looking at some of these content issues, key concepts, is that g is concave down where g prime equal to f is decreasing. So, okay, hey, I'm going to try to get fancy here a little bit. I'm going to see if I can switch colors. That would be from -2 to 0. Let's see, where else is it decreasing? Oh, yeah, over here, from 5 to 7. So I just have to see where these intervals overlap. And that's not too bad. That's -2 to -1 and 5 to 7. And those are the intervals where g is increasing and concave down. That is a very typical sort of a question on recent AP exams. Classic way to solve that one. Let's take a look at the scoring guidelines. So here are our expected scoring guidelines for Part C. A typical guideline here is that this kind of a problem is worth 2 points. 1 point for the answer, which is the 2 intervals, and 1 point for the reason. So on these videos, we talk about our scoring guidelines, and then I present what I call scoring notes, and these are interpretations. So these are interpretations that will help you understand how points are awarded and to help your students prepare for the next AP Calculus exam. The first point is earned for the answer, and it's earned for the correct intervals, and darn it, you have to have both of them. And even though I think in the question it said, what are the open intervals? The intervals can be reported as open, closed, or you know what, even half open. We're not going to worry about the endpoints, at least not in this problem. I would in my class, but we're not going to worry about them in this problem. And often in AP Calculus exams, we have an eligibility criteria. So the student must earn the first point in order to be eligible for the second. Now, often there are some exceptions, and there are here. So it is possible for a student to earn 1 point in this problem, but I can't really follow what's on the right-hand side up here. And here's how they might do it. If a student reports only 1 correct interval with a correct reason, they would earn 1 point in this part. Now, a reason that references or uses only G prime is eligible for the second point. However, a reason that uses only F is not eligible unless the student has made a connection here, has somehow told us, conveyed to us, this fundamental theorem of calculus idea that they know that G prime is equal to F. Now, there are a couple of ways that a student can convey that G prime is decreasing. And here are some ways that we've seen accepted in past exams. G double prime is negative. The slope of G prime is negative. And let's see here. In this case, references to the function or the slope or it are just too vague here. So remember, good communication, good notation too, but good communication is important. So these sorts of references aren't good enough. The student has to tell us, well, what function are they really talking about? So that takes care of part C. D and E are a little bit quicker, but about some of my favorite topics. So part D here, we need to find the value of G of -1. And there's that phrase again, show the computations that lead to your answer. So here are the 2 most important concepts, I think, that are needed to solve this problem. And I think the first one is that a definite integral can be interpreted as what I call net area. So the definite integral from a to b of f of x dx is a1 minus a2, where a1 is the area of the region above the x-axis and below the graph of f. a2 is the area of the region below the x-axis and above the graph of f. So in order to solve this problem, I think that we should use geometry to find areas. This is a very typical sort of a question, and I believe that's what they would like us to do to solve this. Now, the truth is, in correcting many of these problems, some students may actually attempt to find an algebraic expression for f. If you remember back to that graph and what it looks like, it's a piecewise, it would have to be a piecewise defined function. And some students will actually try to find an algebraic expression and then actually an analytic antiderivative. Now, although that would work, it's just not a judicious, a good approach to this problem. Now, the second concept that I think we need here involves the reversal of the limits in a definite integral. So take a look down here at the bottom. If I reverse the limits of integration, I need to attach a negative sign out in front. Some people call this a property of definite integrals, but you know what? I think you can get this result just by thinking about Riemann sums and the definition of delta x as the width of each subinterval. In any event, this is an equality. If we reverse the bounds, we need a negative sign out in front. So let me show you how I would attack this one. Here's the graph of f once again. G of minus 1, let's see, is equal to this definite integral. Where did that come from? Well, that's the definition of G that was given to me in the statement of the problem. So the very first thing that I will do is I will reverse these limits of integration, and when I do that, I'll put a negative sign out in front. Now look, this problem can be solved without reversing the limits, but this is just my preference. I find it easier to solve these if the limits are with a smaller value down below, where A is less than B. I find it easier to compute the net area when the limits are like this, with A less than B. So now, in order to find this, I need to figure out the area of that shaded region up here in light blue. And, darn it, I need to attach a negative sign because the region is below the x-axis. So I'm sorry this is a little messy, Michael, but here's this negative sign. Here's another negative sign because this region is below the x-axis, and the area of that region is just the area of a right triangle, 1/2 the base times the height, 1, 2, yep, I think that's right. And after all of that, son of a gun, the answer is simply 1. So, okay, the scoring guidelines here are very straightforward. We're going to give just 1 point for this one and 1 point for the answer. But I'm going to add in here, supporting work is needed. You know, we've gotten much farther away from accepting what we call bald answers. A bald answer is an answer alone where some supporting work is expected. So a bald 1 here, that means a number 1 that appears alone on the page would not earn the point. I know there's an argument, it's the right answer, and I know you have some great students who can look at this problem and just see it right away. Might do a little scribbling on the graph on their paper and come up with 1. But we are encouraging, we almost demand good communication here. So there must be some supporting work to convince us that the student is using an area argument to arrive at this answer. And let me finish up kind of quickly by looking at part E here. This one is we want to find another value. We want to evaluate G of 2. But the geometric region here isn't quite as simple. So once again, I've added in the graph of f. I've repeated the graph of f. And G of 2 is by definition this definite integral. 0 to 2 of f of t dt. This definite integral represents the net area of this shaded region up here in light blue. Well, note that this area is entirely below the x-axis, so I'm just thinking out loud to myself as I solve this. When I get an answer here, darn it, it better be negative. Now, it's not a nice geometric region, that blue shaded area. It's not a nice region like a rectangle or a triangle or even a trapezoid. But I think I can find the area by finding the area of a square. Sorry, this might get a little messy, but I'm going to find the area of that square, and then I'm going to subtract the area of that quarter circle. So here's that calculation inside here. Here's the negative sign out in front because, well, darn it, that region is below the x-axis. And I think with a little simplification, I got a pi minus 4. How about that? That's kind of cool. So the scoring guidelines here, we're going to make this problem worth 2 points. I think that's pretty reasonable. 1 point for using the area of a quarter circle in the calculation. So we want the student to recognize that they've got to use the area of the quarter circle in some way to get this answer, and we want them to convey that to us. And 1 point for the final answer. Now, a reminder here that the response does not need to include a definite integral. In other words, I don't really need to see this on the student's paper. I'd like to, but I don't need to for full credit. The student can go directly to area calculations. Now, the correct answer with pi minus 4, with no supporting work, will only earn 1 point here. So if pi minus 4 just all of a sudden appears on the page, again, you have some really good students, that's only going to earn 1 point. Remember again, I'm sorry about this, but remember again that we are stressing communication skills. And finally, if the answer is wrong, but if there is enough evidence that the area of the correct quarter circle is being used in a reasonable way in the calculation, subject to some professional judgment, that would earn 1 point. Well, okay, I hope that gives you a good idea of how to solve these problems using the necessary AP Calculus concepts and an idea about what these videos would look like, a reasonable expectation of how these problems would be scored. I'm going to try to turn this over to Tom now, who's going to do a little bit with technology.
Okay, thanks, Steve. We'll
Okay.
see if we can handle this pass off here.
All right, let's see. Oh, here we go. All right, and here we go. Tom, where are you? Where are you? I don't see you up there. Are you listed as Texas Instruments?
No, as TD, Tom Dick.
Oh, I don't see you up there. Where the heck are you?
There we go. I think you did it successfully.
I did it. All right, there you are, sir.
All right. And you all can give me some feedback if this is working. I'm hopefully getting my TI-Nspire screen up. Mike and Steve, is that looking all right?
I don't see it yet.
Okay. Let's see.
There we go. Looks good, Tom.
Okay. All right. Well, this graph should look familiar to you. It's exactly the graph Steve was working with. And what I'm going to do is try to illustrate a few things, some of the ideas we try to communicate in our tech videos. I did want to say a word about Steve and I, when we began the TI-Nfocus AP Calculus project, we made a really early decision to organize things around the release free response questions each year. And one of the reasons for that is certainly they're of interest to people, but we see those exam questions, the released ones, they become teaching tools the next year or in subsequent years for teachers to come to. And this year was very special. We didn't have any release questions, but College Board was okay with Steve and I coming up with some mock questions that we think are pretty representative of the ideas from this year's exam. These graphical STEM questions, we sometimes call them, where a function is presented graphically without a formula, those have been really popular on AP exams. I think there's been a question similar to this on almost every single exam in the last 20 years. And they're often very simply geometrically described graphs. Again, there's no formula given, but for example here, this graph is made of line segments and pieces of circles, quarter circles. Now, on the 2020 exam, it was actually completely open technology. People could use whatever technology they wanted. However, with the graphical and tabular questions, there were some occasions where people could use a calculator, but it was fairly minimal. I'm really looking at this now as, if I have this graph, how can I use that to discuss some important calculus ideas with my students, and how might I use the technology to help me in that discussion? So as Steve said, some students actually take that graphically presented function and figure out an analytic formula for it. And I've done that here. I've actually gone into, I'm using TI-Nspire. I will do an example a little later with the TI-84, but my Nspire, I've actually entered this function as a, I'll show you the formula for it. So it's this ghastly piecewise defined function, and you can see there's some linear pieces to it that corresponds to line segments, and you see some radicals, so that's corresponding to the pieces of the quarter circle. So it can be done. So I kind of reverse engineered that graph so that I could come up with this nice graph here. But graph like that, now that I've got it presented, I'm going to play two roles for this blue graph. The first one, both of which were relevant to this question that Steve was discussing. One of them is, I just like to know as much as I can about what does the graph of the derivative of this function look like? So that's a pause. I'm letting you think about that a bit. And let's just kind of look at it, and then we'll let the technology confirm for us or perhaps show us where we've gone wrong if we've made any mistakes. So here I've got a linear graph for this piece, and it looks like it has a slope of, let's see, over 1, down 2, I think a slope of -2. My derivative graph, I would actually expect to see a constant function with a y value of -2 here over this interval from -2 to 0. For this quarter circle, wow, over here at the start of the quarter circle, this is a very, very steep positive slope. So my derivative graph, I would expect it to be a really large y value positive. That slope continues positive, but it comes to 0. So I would expect my derivative graph to come down to 0. It's positive and come down to 0. And then I have another quarter circle. Same thing again. It's going to start out very tall positive, very large positive number with a very steep positive slope. Come down to 0. And now we have this kind of change in from what we've got here. We're looking at the derivative. This is changing from increasing to decreasing. So this should be, what do you think? What's going to happen here? Oh, well, my derivative suddenly changed to a constant again. It suddenly changed to a negative slope of, I think this slope is actually, let's see, we've got a run of 2, decrease of 3, slope of -3/2. So I should be seeing a horizontal line segment, y value of -3/2, suddenly changing to a y value of +3/2 for this line segment. Now that's a lot to keep in mind. But what I'd like to do now is, as we talk through that, let's actually now take a look at what the derivative looks like. And you might say, oh my gosh, you have to go to that analytic form and do all kinds of calculations on all these pieces. No, not at all. What we can do is, for our F2, let's just pull up our symbol palette. And there's a derivative. I'm just going to ask it to calculate the derivative with respect to x of f1 of x. And that was that ghastly piecewise function. So let's let it go to work here. Because it's piecewise, it's going to be interesting. And here's a little tidbit here. This function, you can do exactly what I've done here on the TI-Nspire. And, but it'll actually graph faster. That's because it's doing a numerical derivative. I think this one is doing, because it's piecewise, it's doing a lot of analytic work with the CAS on all these pieces.
Tom, there was a question in the chat. I just want to take care of if it's okay. Somebody
Sure.
said that it looks like the graph is different from the previous example. It may look that way, but those numbers, -2.5 and 9.5, are actually the endpoints, I believe, of the axis. Is that correct, Tom?
That's right. So this last hash mark you see right here is actually -2, and the -2.5 refers to the left edge of the screen. Similarly, over here, that's +9, which was where your interval ended, I think. And the 9.5 is the right edge of the screen. So there we go. And I think we did a good job of interpreting what this graph should look like. So very neat. Okay, now I'm going to turn the tables here, and let me basically go up and turn off this function. Okay, so I've turned off F2. Oops, turned it back on by accident. There we go. And I want to do an F3 where now I'm going to look at this blue graph in the way it relates to G. The function G that Steve was discussing was a definite integral function based on this. So it was an antiderivative. So I'm going to actually put in the formula for G into F3 here. So let me go back to my palette, and I think we've got a definite integral palette here. And I think the lower limit of integration was 0. The upper limit of integration was our variable x. And then I'm going to put in our F1 of x. This is not the best form to use the same variable as dummy variable, but it really doesn't hurt. And so now we're going to actually get a complete graph of G, which there were several questions about in the problem Steve was discussing. So let's take a look. Let's see what I hit. There we go. And let's take a look at this and see if it's making sense to us. Where my blue graph is changing sign from positive to negative, if that's the derivative, my black graph should have a local maximum there. And where my derivative graph just suddenly changes from decreasing to increasing, we should see an inflection point here at 0. Now, the graph from 0, all the way through both quarter circles is increasing. So my graph should be concave up. See, are there any other points of interest off the screen? Well, I think so. Here at, let's see, is that 7? No, at 5. At x equals 5, my derivative is changing from increasing to decreasing. We should expect to see an inflection point. And also here at x equals 7, we should see an inflection point. I'm going to just go ahead and move the graph down. And it's taking a while to compute. Let's see. I kind of moved it over, but I think you can see these. Here we go. There was an inflection point around here where it changed from concave up to concave down, and now we see this other inflection point. So that's all bearing out. All right, and so that's something I really like to do with a lot of these questions is with the graphical stems is go ahead and do my best to reverse engineer them and pose them on the software or calculator, and then ask these questions. And the questions are really about reading the graph and then using the technology and then to check and see if we interpret it correctly. Okay. Steve, anything you want to say before I switch gears over to the 84?
Sounds great, Tom. I think the TI-Nspire does some great stuff. That is a cool example that it can actually define. You can define a function using a definite integral, and you can actually graph it and see the relationship between that function and the original. Very cool.
And I want to be quick to add, you can do exactly this on the 84 too, because it's going to do a numerical derivative and a numerical definite integral, both of which are going to be within its capabilities. It's just the Nspire, there is an option to use CAS if you've got one of those machines.
Yep.
Okay. So I'm switching platforms here over to the TI-84. And this is another one of our mock exam questions that Steve did not discuss. One of them had to do with a table of values where the values were some selected time values, where time was in seconds, and some y prime, or derivative of y values, in meters per second. And so I've got the values that were in the table that were presented in the problem, and I've gone ahead and entered them in the TI-84 as named lists. So this is the list of times that were in the problem, and these are the y derivative values. So if we're thinking of a particle moving along the y-axis, we're given these velocity values. Okay. So in that context, notice that I've entered them in the stat editor in lists, which means we could go and do a stat plot of these values. And that may be something you don't think about doing often in calculus. You usually use the y equals menu, but here's a case where we're going to use a stat plot. Let me go ahead and enter that, see what our settings are here. So we've got time along the horizontal, the derivative values of y that we were given. And I'm going to plot this as just a scatter plot. And let's just take a look at it. And there it is. There's those values that were in the table. And if we trace them, we can see the time and y derivative values paired up. They're not actually equally spaced. Some of them are, but we go from x equal 2. That x is actually our time. Jumps all the way to 6. Y equals -2. The y values here on this graph are corresponding to velocity values. Okay. Now, one of the questions asked in our mock AP question was, okay, I've got a derivative value. Let's see. I've got a velocity of 8 at time equal 2. And I've got a velocity of -2 at time equals 6. Could I approximate the acceleration at time t equal 4? Okay. Now, to visualize that, I'm going to go back to the stat plot and actually make it a different type. Instead of just showing the dots, let me connect the line segments. And so now I've connected the dots. And the reason I did that was one of these line segments helps me visualize what I'm really after. I'm going to do if I'm going to approximate the acceleration at time equal 4, what I could do with the data given is approximate the rate of change of y prime at 4. And the two nearest values are at t equal 2 and t equal 8. Excuse me, t equal 2 and t equal 6. I misspoke. 4 is right in the middle there. So I could, if I find the slope of this line segment, that would be a good approximation for that acceleration value at time t equal 4. And we could just go to the calculator menu and calculate those values. Let me see, I'm going to have to go back here. We had what, -2 at 8, or it's, yes, -2 at 6. I keep misspeaking. And then this other value is 8 at 2. Okay, so we'd have -2 minus 8. Divided by 6 minus 2. Didn't misspeak that time. And there we go, -2.5 was our approximation for that acceleration. And units there would be meters per second squared, given the units that were provided. The last thing I think I'll show you is I'm going to take a shift over here to a BC kind of question. Go back to the stat editor, back to my data, and a BC type of question here would be, suppose we know the y position at time t equals 12 is -3. So it's at the y coordinate position -3 at t equal 12. I'm going to use these lists over here to work with that. Let's see, let me go ahead and enter 12 into the first line of L1. And in L2, let me enter -3. That's kind of the value that the one initial position that we were given at time t equal 12. And let's say we're asked to use Euler's method with steps backing up 2 units each time and approximate the y coordinate at time t equal 4. So these lists here actually become kind of a workspace for us to do Euler's method. So I'm going to use L3 to figure out what kind of increment I need to add on to my initial position to get the position at time t equal 10. So at time t equal 12, our derivative is -5. I'm going to step backwards 2 units. So my increment will be -5 times a step of -2. And that means that at time t equal 10, I will have moved from t equal 12, 10 units. So I'll go over here at time t equal 10. My new position is the -3 plus that increment of 10. And so I'm at the y-coordinate of 7. And now I just play that game again. Let's see. Again, at time t equal 10, my derivative is -1. So the increment will be -1. Oops, I think I have too many negatives in there. So it's -1, and the step size again is -2. And there's the increment is 2. And so at t equal 8, our new y position is estimated to be 7 plus 2. And then we just keep playing that game again and again. I'm going to stop there, but we can just step our ways. That's I think of Euler's method as kind of doing a running Riemann sum. It's a very similar idea. But I actually like using, on the Nspire, it would be the list and spreadsheets feature. On the 84, you can use the statistics editor. It gives you kind of a spreadsheet space in order to work with. So it's very, very handy. Okay. Let me hand it back to Mike Houston, who will see us on out here. So let me see if I can stop sharing and pass it over to Mike.
Thanks so much, Tom and Steve. As we begin to wrap things up tonight, if you have any last-minute questions, please try to get those asked. I know Tom and Steve will do their best to get those questions answered. To receive a certificate of attendance for tonight, go ahead and click the link that appeared in the chat window. Also listed is the link for the documents from tonight. And if you're watching this on demand, go ahead and copy that link into your favorite browser to receive your certificate. If you happen to have any issues with either of these two links tonight, just hang tight. You'll automatically get a follow-up email in a couple days, and that follow-up email will contain a link to the recording, so you can go back and view this at your own pace, as well as links for the certificate and documents as well. We'd love for you to stay connected and continue the conversation that you may have seen tonight, and feel free to do that on any of the major social media outlets. If you're in need of any post-webinar follow-up, feel free to give us a call at 1-800-TI-CARES or send us an email, ti-cares@ti.com. We'd love to hear from you. Lastly, when you leave the webinar tonight, a brief survey will automatically appear in your browser. Your feedback helps us plan future online events, so we really hope you share your thoughts in the post-webinar survey. Big thanks to Tom and Steve for everything they put together tonight. We really appreciate it.
Thank you, Michael. Thanks, Tom.
Thank you.
And thanks so much to everyone for joining us tonight. We'll see you back online next week. Please stay safe. Have a great night.